number 45. Profit at time t is given by negative t cubed plus 9t squared plus t plus 5. And they want you to restrict your attention to the interval 0 to 6. Well, how about if I try to do it in general and then restrict myself? So let's see what happens. Let's pursue it as before. Our first derivative information p prime gives us negative 3t squared plus 18t plus 1. Yeah, shoot, I hate to have to use the quadratic theorem again. So we set this equal to 0, shoot. And in order to find t, it doesn't factor nicely. So t is, remember, negative b plus or minus the square root of b squared minus 4ac all over 2a. So in this case, our a is negative 3, our b is 18, our c is 1. So that's negative 18 plus or minus the square root of 18 squared minus 4, a is negative 3, c is 1, all over 2a is negative 6. Yeah. 18 times 18. $324. Negative 18 plus or minus the square root of 324 add 12, 336 over negative 6. Yeah, now I see why I struck the problem out. This thing is like 18 and a half. Yeah, they hadn't wanted you to do this in general, because you see, those are not in the interval 0 to 6. Yeah, phooey. For fun, I'm taking the second derivative. Negative 6t plus 18. Yeah, that's what they're after. Set that equal to 0. Yeah, okay. To try and make sense out of the problem, t equals 3 is your one inflection point. So this graph is doing something like Here at 3, you have an inflection point. And the point of the problem was, an inflection point is, in economics, called your point of diminishing returns. And the reason why is, this is your profit function, okay? So yes, your profit is increasing as you go from time 0, 1 year, 2 year, 3 year, 4 year, 5 year, 6 years, okay? As you go through time, yes, your profit is increasing. But notice here, the slopes are positive, meaning that your profit is increasing. The rate of your profitability is increasing. Whereas here at the inflection point, it's leveled off. And so beyond that, yeah, your profit is increasing, but your returns are diminishing. That was the point they were trying to make. And I see why I took it off of the, yeah. Should take it off the syllabus. So I wasn't expecting that to be so messy. Is 61 any better? Learning curve, let's see. Cost engineers have noted that the efficiency of workers in a plant or on a machine increases over time as the workforce gains efficiency and skill in performing the repeated manual tasks. Hirsch reported that the relationship between the accumulated average amount of direct labor input, V, on a textile machine and the cumulative number of units produced, X, is given by, find the first and second derivative, sketch the graph. Hopefully, that's not going to be as bad. Let's take a look at 61. So y is equal to ax to the negative 0.175. Okay, the point of the learning curve. The more often you do something, the easier it becomes. So X is the number of labor hours, and Y is the number of goods produced. And it says find the first and second derivative and sketch the graph. Well, let's see here. So do y dx, first derivative. A is a constant. The old power is the new coefficient. And the new power is 1 less, negative 1.175. And if you set that equal to 0, you don't have any values, right? Because this x is in the denominator. And here in the numerator you have negative a times 0.175. So this has no, so there are no critical points. There's no x will make that 0. So that only means you have one interval. So I just test one point to determine the shape. So the interval is the whole real line because there are no inflection points. So take any number you want. How about 0? F prime at, oh, you can't have 0. Can't divide by 0. How about F prime of 1? Put 1 in there. This is positive, that's negative. So it's everywhere concave down. And now how about your second derivative? You call it y double prime or d squared y over dx squared. Do the derivative again. And so here you got two negative numbers. Negative 0.175 times negative 1.175. Two negatives give you a positive. And x to the subtract 1 again. Negative 2.175. And so notice, two negatives give you a positive. I don't care numerically what it is. I just care about its sign. Okay. Again, I set that equal to 0, but you see, x is in the denominator, can't be 0. So there are no inflection points. So again, there's only one concavity in it, over which I'm going to test the second derivative at one point to conclude something about concavity. One interval. So test any point, let's say 1, f double prime of 1. Positive, positive, positive over positive. So concave up. So you have an everywhere decreasing function that's concave up. Everywhere decreasing concave up. Okay. And sketch your graph. And so that would be a typical learning curve. Asymptotic. Makes sense. So if production doubles, what happens to the average amount of needed labor? Well, doesn't it make sense, just ballpark, if you learn as you do the material, if you double your production, it's going to be less time. So let's say, so to produce y equals 1, what's x? X and negative 0.175. So that's equal to a over x to the 0.075. So that is, solve for x. X to the 0.175 is equal to 1 over a. And so x would be, can't do that with a calculator. Because now if y is equal to 2, then you would have 2a. And that'd be, x would be, so you need less labor, but in order to work this thing out, you'd have to have a calculator. So, no, I should take that one off too, because you don't have a calculator. Okay, but a learning curve, just in general. The more often you do a task, the better you're at doing it. All right, now, let's take a look at 5.3. Or, excuse me, 5.5. So, the big idea here is that practical considerations limit x. You know, we had been having x go throughout the whole real line. But in practice, if x is quantity, you can't make an infinite amount of goods. So there are practical considerations that restrict A. So x is restricted between a couple of bounds. So A being restricted between a couple of bounds makes it easier to find extrema. The candidates for extrema are, well, two varieties. They could be the endpoints, A and or B, or they could be any critical points in the interval A to B. So what this means is, in order to find the extrema, you don't have to draw the thing anymore. I'm just trying to explain why. So you might have the same graph, okay? But if your intervals are different, your extrema might be different. So here in the first one, let's say that A goes from there to there. If that's your interval, then you're only looking at this much of the curve. And in that case, you got a maximum at A, and you got a minimum at B, if that was your interval. But say that this had been your interval. They gave you, say, from here over there. If that was your A and that was your B, you're only looking at this much of the curve. And in that case, this critical point is your max. And this critical point is your minimum. And how about over here? Let's say that they went from, say A is there. So this is continuing on upwards. Say that your A is there, and say that your B is over here. So even though it's the same function, same graph, where the interval is depends upon, or where your interval is influences the candidates. In this case, you're looking at this much of the graph. And in this case, endpoint B is your max, because you see its y coordinate is much bigger than that. But this critical point is your minimum. So that's what I mean when you can have all combinations. So you don't, the good news is you don't have to graph these anymore. All you have to do is check out the candidates. Which is the largest, which is the smallest. And your candidates are your two endpoints and any critical points in the interval. Now, if the critical point's not in the interval, you don't care about it, because you're only looking at the interval. So let's take a look at some problems. Oh, and notice, I have made an assumption here. I have assumed that f of x is continuous on the interval. No jumps, no breaks. If I take my red pen, here's a counterexample. You know, you won't be looking at this situation. Say if your function, like the log function, say it goes asymptotically at 0. You see on the interval 0 to 2, say 2 is here. On the interval 0 to 2, there's no minimum, right? There's no minimum at all. Because the function is not continuous at 0. So typically like 1 over x, we've got to assume that f is continuous on your interval. If it's not, there's no guarantee that you'll have an extremum. So let's take a look at some of these. Number 11. Locate the extrema So here they give you a function, f of x is equal to x squared minus 4x plus 1. And they have to tell you your a and b. You're restricted to the interval -1 to 1. And the problem is find extrema. And you know what I mean by that. You want your absolute max and you want your absolute minimum. Good news is you don't have to graph it anymore. Because the candidates are either going to be -1, 1, or any critical points that are in that interval. So first off, let's ask ourselves the question, are there any critical points of f of x in the interval? Well, let's check it out. F prime is 2x minus 4. Set that equal to 0 and solve for x. That'll be your critical point. And do you agree with me? There's one where x is equal to 2. And oops, 2 is not in my interval. I don't have to worry about it. 2 is not between -1 and 1. I don't have to worry about it. Okay, so secondly, evaluate the candidates. And remember what I said, candidates are the endpoints, A and B, and critical points in the interval. Well, if I've done this right, my one critical point is not in the interval. So my only candidates are -1 and +1. And I want to find out what's the largest, what's the smallest. Plug them in. Arithmetic. F of -1 is -1 squared minus 4 times -1, add 1. Is that 1 plus 4 plus 1? Did you get 6? And now f of 1, 1 squared minus 4 times 1 plus 1. Did you get 1 plus 1 is 2 minus 4 is -2? And so there you go. Here you have an absolute max of 6 at x equals -1. And you have an absolute minimum of -2 at x equals 1. So notice you got a what and a where. What is your absolute max? Where does it occur? I mentioned this, I think, back during graphing. If you ask a what question, and if you ask a where question, what refers to the y coordinate? Where refers to the x coordinate? And you don't have to, but there is a notation here. You could say f sub max occurs at -1 and is equal to 6. You don't have to write this if you don't want to, but you see where it makes sense. I want the maximum value of f on this interval, and it occurs at -1 and is equal to 6. I also want the minimum value of f on this interval, which occurs at 1 and is equal to -2. So in these problems, you've got the what and the where. Let's take a look at 15.
How come we don't test out point zero, like 0, like the number 0, isn't it?
Oh, okay, because, first off, let me give you two answers.
Alright.
Let me give the first answer. What if we tried? What if we plugged 0 into there? Wouldn't we get an answer of 1, which is not maximum and it's not minimum?
Okay.
Okay? And so that is the arithmetic answer. And then the theoretical answer to your question is your only candidates are endpoints or critical points. And x equals 0, it's not an endpoint, and it's not a critical point, because your only critical point is here at 2, which is not your interval. So the only ones you need to test are the endpoints and critical points in the interval. Let's take a look at 15. So here they give us a function f of x is x cubed minus 3x plus 1 And we're restricting this to the interval -1 up to 3. Okay, so the first question I ask, are there critical points in this interval from -1 up to 3? If there aren't, I can ignore them. If there are, they become candidates. So let's find out. F prime of x is 3x squared minus 3. Well, I set that equal to 0. Now, how do you want to look at that? Can you look at that and say to yourself, okay, x could be 1 or -1? If you can do that, fine. I look at that and I think factoring. I factor a 3 out, and I have x squared minus 1. Factor a 3 out, I have x squared minus 1. And then x squared minus 1, that's the difference of squares. So however you think about it, you don't have to do it that way. But however you think about it, you're getting 2 critical points. At x equals -1 and x equals +1. Notice they are both in the interval. These are both in my interval from -1 up to 3. So in fact, the endpoint that I'd test anyway is also a critical point. So it's really a candidate. So now what I do is I evaluate my candidates. Evaluate the candidates, and by that I mean you remember. Who are the candidates? The endpoints and critical points in the interval. Which both of these are. So I need to check out the y-coordinate of -1 because it's an endpoint and a critical point. I need to check out 1 because it's critical, and I need to check out 3 because it's an endpoint. So I've got 3 candidates for my extrema. It must be among them. Arithmetic, just plug it back in. You got -1 cubed minus 3 times -1 add 1. Or -1 add 3, +1. Did you get 3? F of 1. 1 cubed minus 3 times 1 add 1. Is that 1 plus 1 is 2 minus 3 is -1? Did I do that right? And here I have 3 cubed minus 3 times 3 add 1. So 27 minus 9 is 18, add 1 is 19. And so you look at those 3 numbers. Your extrema must be among them. Spot the smallest, spot the largest. Smallest is -1. So you have an absolute minimum of -1 at x equals 1. And 19 is the largest, absolute maximum of 19 at x equals 3. Or if you want, you could write f sub min occurs at 1 and is equal to -1. F sub max occurs at 3 and is equal to 19. And so in fact, this guy was neither. Even though it was both endpoint and critical point, it's neither extremely. Now, I'm going to save problem 29 for next time. Because what they do is that they give you the same function, and they give you 4 different intervals. And remember what I said about continuous. A moment ago, we looked at this situation. If your function is not continuous on the interval, all bets are off. There would not necessarily be extrema. And so in problem 29, we'll do that next time. The first interval is legal. The second interval, it would embrace 0, and you got x to the negative 3. Oops, that's not legal. C, it's not a closed interval. It's open at 0. Same problem. And D, well, same problem. It's an open interval. So we'll do 29. Only part A will work like these. B, C, and D, I'll draw pictures and show you, oh, these situations don't work because it's not continuous over a closed interval. Okay, but for now, the next section is very important. And I've set aside a couple of days for it. But let me do a problem now. So we're talking about 5.6 optimization. And optimization is itself half the reason why you business people have to take calculus. Optimization means you are trying to optimize something, and in context, that means either maximize or minimize. So in context, the word optimize means either maximize or minimize. For example, if I want you to optimize your profit, you want to make your profit as large as possible. If I ask you to optimize your costs, you want to make your costs as small as possible. So you want to maximize profit and minimize cost, and both of those come under the word optimize. Okay? Now, you all hate this chapter because it's word problems. And you all hate word problems. Yeah. Let's start with an easy problem. So let me do an easy example. You have 400 yards of fencing, like cyclone fencing. You want to enclose the largest possible rectangle on 3 sides. In other words, you are using a natural barrier on the fourth side. So for example, let's say you're at a park. Park's by the river. What you want to do is you're fencing off a parking lot. And so you want to fence off a rectangle on 3 sides. You can use the river for the fourth side. What you have is 400 yards of fencing. And the largest rectangle refers to area. So in all of these problems, you've got 2 pieces. One piece is called your constraint. The other piece is called the objective function. So constraint. There is something which is constraining you. You know, if you're trying to maximize your profit. Something is constraining you, otherwise you could make an infinite amount of money. There's something limiting you. That's called your constraint. And so here in this case, your constraint is you only have 400 yards of fencing to work with. And the other half is the objective function. The objective function is the thing you're trying to optimize given your constraint. So in this case, you want to build the largest possible rectangle. Isn't that area? Okay, isn't that area? And so I somehow need to link my constraint with my area. And how about this? Let me call x the width of the rectangle. Let me call y the length of the rectangle. And of course, since it's a rectangle, that width is also x. And so what's the relationship between x, y, and my constraint? Well, I have 400 yards of fencing. X plus y plus x. That's all I got. My 400 equals 2x plus y. And so what's the thing I'm trying to optimize? I'm trying to optimize my area. How do you find the area of a rectangle? X times y. Now, do you see that here I have 2 variables? I have expressed my constraint and objective function using 2 variables. But you know, here in chapter 5, in the problems that we've done so far, we have found the optimum by taking the derivative. And you can only take the derivative if you have 1 variable. Oh, there is something called multivariable calculus, Calc 3, 2110, but you probably don't have to worry about that. To take a derivative, to find optimal, take derivative but I need 1 not two variables. So I need to eliminate. Solve the constraint to eliminate one variable. So does it make sense? Y is equal to 400 minus 2x. So solve the constraint for y, and then I'm going to put that expression for y into my objective function. And then I can take a derivative. Solve the constraint to eliminate one variable and plug this into the objective function. So my area is equal to x times y, but y is now 400 minus 2x. So my area now as a function of x, how about if I simplify, is 400x minus 2x squared. So I take the derivative, which is 400 minus, that's 4x. And you know that optimum occurs at critical. So set that equal to 0. Solve for x. Is it clear, right? 4x equals 400. X is equal to 100. So that's probably my maximum. But just to be sure, if that critical point is a maximum, tell me something about concavity. If this is a maximum, what do you want concavity there? Down, right? So let's check concavity. A double prime is -4, which is negative, so it's concave down. So max at x equals 100, and the only other thing left to do, what is the y? You need the dimensions. Y is 400 minus 2x. Y is 200. So if these are your constraints, your parking lot needs to be built with a width of 100 and a length of 200. Okay? So optimization problems are extremely important, and they're half the reason why you are condemned to taking calculus. And what makes it so much fun is they are word problems. You love word problems. So you can start looking at 5-6. Finish off 5-5. You can start looking at 5-6 for Wednesday, see you Wednesday.
Yes, sir.